Hello and welcome to the GCSE Chemical Changes topic with Mrs. Castanera. We're on lesson 9, Electrolysis. Today's key words are ion, electrode, anode, cathode, electrolyte, molten, solution and redox. So I'd like you to start the lesson by doing the 8 knowledge check questions, please. So pause the video whilst you do that. So let's go through those. Question 1. Metals become positive ions because they lose their electron. Non-metals become negative ions because they gain electrons. Expand the acronym OILRIG. So oxidation is loss, reduction is gain, so it's OILRIG for OILRIG, and we mean of electrons for those. State where we find valence electrons. Well, in the outer shell of the atom. Ions can form a giant ionic lattice or giant ionic lattices. A solute plus a solvent turns into a solution. An electric current is the flow of electrons, and the type of bonding between non-metals is covalent bonding. So give yourself a mark out of 8, please. Okay. We're going to move on to the overview. So today in our lesson we are going to be able to, by the end of the lesson, explain why solid ionic compounds cannot conduct electricity. We're going to be able to define the key terms used in electrolysis, and we're going to be able to explain what happens to positive and negative ions in electrolysis. Ionic compounds. Atoms will react and form bonds with other atoms in order to fill up their outer shells, which is in the highest energy level, and makes them become stable. Okay, so they're stable because they have filled their outer shells. Okay, and so that's why they are now stable, because with a full outer shell, they are complete and they are no longer trying to lose or gain electrons. Okay, so metals form positive ions, also known as cations. We're going to write that in here. Okay, by losing their valence electrons, remembering that the valence electrons are from the outer shell, so they're electrons in the outer shell. I'm going to write that over to one side here. Okay, so it's electrons in the outer shell. Non-metals form negative ions by gaining valence electrons. Okay, so they form negative ions, the non-metals, by gaining valence electrons. And these negative ions are called anions. Okay, so they are negatively charged and cations are positively charged. And I remember this as cations, the T in cations reminds me of the plus symbol. Okay, so this T in cations reminds me of the plus symbol, and anions is the other one, it's negatively charged. And those valence electrons are in the outer shell. So positive and negative ions are attracted to each other. We know this, okay, because they're oppositely charged. And the reason they're attracted is because of these electrostatic charges. What they do is they attract to each other and they form an ionic compound with ionic bonds. Okay, so ionic bonds are very strong because it's positive and negative charges with electrostatic forces. Ionic compounds can form giant structures called a lattice, also known as a giant ionic lattice, which has a regular and repeating pattern of ions. The ions within the giant ionic lattice are fixed into position, okay, and that is because of the ionic bonds. Okay, and they are very, very strong bonds. So an electric current is the flow of electrons through a material. For a material to be considered a conductor, that's something that conducts electricity or allows electrons to flow through it, So for a material to be considered a conductor, there must be free delocalized electrons available to move around. Okay, so not all materials have this, only metals or only conductor materials have this. And metals are an example of a conducting material with free delocalized electrons. E.g. metals. So move that over so you can read that. Okay, so in the giant ionic lattice, there are no free electrons. Okay, so a solid ionic compound cannot conduct electricity. Okie dokie. That means that, so delocalized electrons are electrons that are able to move, okay? So delocalized means able to move around. They are not locked into place, stuck around a single atom. Okay, so the reason they can't conduct electricity is because we cannot make the electrons move because they are solidly stuck to each individual atom. Okay, and those electrons need to move to carry current. I'm going to write a little note here. Okay, so because E minus, that's the symbol to represent electrons, need to move to carry current. Okay. So, getting ionic compounds to conduct electricity. This is our title, our subheading. Okay, so heating an ionic compound, okay, provides enough energy to overcome the bond energy. So by heating it, if it's an ionic compound, that gives enough energy to overcome the bond energy, and that means it breaks or weakens the bonds. Okay, so we're going to write that in here. Breaks or weakens the bonds. Okay, now, and that bond energy is between the ions. So it breaks or weakens the bonds between the ions. This means that those ions are then free to move around, and we say it has become molten and it behaves like a liquid. Okay, and this is very similar to melting a substance. Okay. So the polar nature of the water molecule, remembering that it has a slightly positive and a slightly negative pole, it's got one of each, and that we represent those with delta negative and delta positive. Okay, so the polar nature of the water molecule, and there's a diagram several lessons back. This causes the ionic bonds to break because of these oppositely charged poles, which then allows the ions to move in a solution, and this process is called dissolving. And we've shown this before and we've looked at this. So heating and dissolving are two ways of breaking the ionic bonds and allowing the ions to move freely. So this liquid is now called an electrolyte. And an electrolyte is an ionic compound that is dissolved in water or heated until melted. So we're going to write a little definition there. So if you'd like to add this to your page, please. An ionic compound that is dissolved in water or heated until melted. That is what the term electrolyte means. So the randomly free-flowing ions can now conduct electricity. Okay, so those randomly free-flowing ions can conduct electricity now. Even though there are no free electrons, okay, the movement of ions performs a similar role to electrons because it's the movement of charged particles. Okay, so we're going to write a little note to say that's because they carry charge. Okay, so because the charged ions carry the charge. Now we have a video here which we're going to watch to learn more about ionic compounds. So if you have a digital copy of this book, you can just click on the link. If not, you're going to want to go to YouTube and type in Fuse School Ionic Compounds and Their Properties, and that should bring you up the video. Or if you just type Ionic Compounds and Their Properties, that should hopefully bring you the video, and you're going to want to select the one that's by Fuse School, which is a channel. So pause the video whilst you watch the YouTube video. So by now you should have watched the video and have a much better understanding about ionic compounds and their properties. So we're going to move on to learning activity 1, dissolving ionic compounds. So we have a diagram here which is of a giant ionic lattice. So this is a solid ionic compound. Okay, so we're going to label that. Okay, and as you can see, it has a regular structure and it is arranged with positive and negative atoms, or ions in fact, alternating. So every positive ion is surrounded by negatives and every negative ion is surrounded by positives. Okay, so this structure here, this is a giant ionic lattice. Okay, it is a solid, it is ionic, and the positive and negative charged particles are bonded to each other through ionic bonding, and that is due to the electrostatic charge and the electrostatic forces of attraction between particles of opposite charge. So sometimes when I do this, I colour in all of the particles that are negatively charged in one colour, say, and all of the positively charged particles in another colour, and that can help you see the arrangement. Now I'm not going to do that. If you want to, you can. So we're going to move on to what this looks like when it is molten and when it is dissolved. So here we have 2 diagrams to show us what the particles look like when they are molten, which is simply when they are heated, okay, and when they are dissolved, which is in water. Okay, and you can see the water particles in this diagram. Okay, I'm going to use a blue highlighter just to indicate which ones are the water particles. They look like little Mickey Mouse heads. So this here is a water particle, and this blue is very dark, but you get the idea, okay? So our water particles are here, and they're highlighted in blue. So in the molten example, where it's been heated, the bonds have been weakened, and you can see that because of the distance between them, okay? So they're not fully broken, they're just weakened, and that allows this to flow like a liquid. So we're going to write this as a note here. Okay, so please make these notes as well. Now for our dissolved in water example, we've got the ionic bonds have been broken fully, okay, and so they are free to be separated later on by electrolysis. So the ions have been fully separated by the polar charges on the water. So first of all, the ionic bonds have been broken. Okay, so as you can see, when it's been dissolved in water, the ionic bonds have been fully broken and the ions have been separated by the polar charges of the water molecules, remembering that they have a negative and positive end. So this end here is delta negative and this end here is delta positive. And that is because the electrons collect at this end here, the spare electrons that are left over from the oxygen, and the positively charged hydrogen nuclei are up this end. So we have our positive ends, which is up by the Mickey Mouse ears, and we have our negative ends by his face. Okay, so that is working to separate the ions in water. So make sure you've got that written out and drawn out. Then we're going to move on back to the book, back to the next step. Okay, so we're learning about electrolysis now. So there's a video for you to watch. It's on YouTube and it'll tell you much more about electrolysis. So if you type in what is electrolysis, preferably with Fuse School in front of it, and you're looking for the Fuse School video about what electrolysis is, and that is on YouTube. So pause the video whilst you watch that YouTube clip. So hopefully you have a much better understanding about electrolysis and how it works now. We're going to run through a bit of explanation and we're going to do another diagram. So we can use electricity to generate a positive and negative area within an electrolyte. Okay, and that is for the ions to move to. Okay, so as you can see, I've written that we can do this to generate these negative and positive areas and for the electrolyte ions to move to. And they can do this because those ions are no longer ionically bonded together. Remember, the opposite charges attract, so your positively charged ions are going to move to the negatively charged area using the electricity, and the area that's been turned into a positive area with electricity is going to attract the negatively charged ions. Now, we set up an incomplete electrical circuit using a direct current. Now, a direct current is made using a battery, okay, and you can set this up, and that means that the current always flows in one direction. Okay, so I've written that as a note here. So make sure you use a battery to produce a direct current, and that direct current, or DC current, in fact I'm going to write that in, DC current flows in one direction only. Okay, so that means that the area that is positive and the area that is negative would stay positive and negative all the time. If we accidentally used AC current, this whole process wouldn't work because AC current alternates rapidly between positive and negative. So the positive area would be rapidly flipping between negative and positive multiple times every second. So that would not work for this purpose, which is why we must use direct current to maintain those areas of positive and negativity. So, as we've said, this means that the electrons flow in a single direction, okay, through those wires, and then also through the molten liquids. So the design of the circuit produces a positive electrode, known as an anode, and a negative electrode, known as the cathode. Okay, and that's one at each end. The Greek origin of the electrodes essentially indicates the direction of currents, the direction of the flow of electrons in the circuit. Okay, so talk about way up and way down. We're not going to worry too much about that. Okay, so these cathode nanodes, they're placed into the electrolyte, okay, which is either molten substance, where it's really hot, or it is dissolved in water. Okay, and the circuit is turned on. Lovely. So this means that our positive ions are going to be attracted to our cathode, which is negatively charged, and our negative ions are going to be attracted to the anode, which is positively charged. When the ions arrive at an electrode, they are discharged. Okay, this is important to know. That means they lose their charge and they become atoms again. Okay, so the learning tip here is positive add anode. Okay, so when the ions arrive at the electrode, they're discharged, they lose their charge, and they become atoms again. So we're going to have a look at this in diagram form. Okay, so I'm going to put that up there. I'm going to zoom out so you can see all the notes. Okay, so I've zoomed out so that you can see all of the notes from this. So I'll just give you, if you want to pause the video briefly to make sure you've copied it all out, and then we'll move on to the diagram and labelling. So we're going to have a look at labelling the diagram of electrolysis. Now we start out here with our DC supply. So our DC power supply here, which is provided usually by a battery, and we have our cathode, which is negatively charged next to the negative terminal, and our anode, which is positively charged next to the positive terminal. So as you can see, we have our container here, which might be something like a very large glass basin, and inside the container we have a liquid, and this liquid is the electrolyte. Okay, now this electrolyte is a molten substance, so that could be something that's dissolved or it can be something that's been heated. So we're going to look at an example of sodium chloride. Okay, so sodium chloride, I'm going to write that up here. And the symbol for that is NaCl. Okay, and that will break apart in solution when it's dissolved in water into Na plus and Cl minus. Okay, and we'll get two separate ions there, Na plus and Cl minus. So let's have a look what happens. Let's start with, they'll be spread out evenly in the solution in the, as dissolved particles. But because we introduce the positive anode and the negative cathode, what starts to happen is those ions are drawn towards the oppositely charged piece of metal, the anode or cathode, depending based on the electrostatic charges that they have and the attraction between those. So let's draw that. So as you can see, I've drawn it so that the chlorine atoms, which are negatively charged, are drawn towards the positive anode due to the electrostatic attraction. That's a force between the two oppositely charged ions and the oppositely charged ions in the anode. So let's colour those in just to show that they're clearly a different thing. So we can see here that I've clearly marked which one's a sodium and which one's a chlorine. And so what's going to happen here? Well, when they join up to the anode, they will lose their charges, okay? They will discharge and become atoms again. And what that means is that the chlorine is going to turn into atoms, and the chlorine atoms go around as a diatomic pair, which means they wander around as Cl2. Okay, now Cl2 is a gas. So what's actually going to happen here is that chlorine gas is going to vent off of this. So it's going to smell a bit like a swimming pool, which is why we usually don't do this experiment for very long. And in fact, you'll get quite a bit of chlorine coming off this experiment, okay? And that is a diatomic particle of two chlorines together sharing their outer electrons. Now, sodium. So the sodium, okay, is going to turn into sodium metal, and it's going to be attached to this cathode. What happens at the sodium end is we get solid sodium forming, so just Na. And it's no longer charged. So this sodium, it's no longer an ion, just either sticks to the cathode and it covers a coating on top of it, or it will eventually drop off and fall to the bottom of the tank or container underneath the underneath where they formed here, underneath that cathode. So you get solid sodium. And we should label this chlorine gas. So this is what happens with the sodium chloride, which is an ion in the water. Now, don't forget, the water itself can also be affected by the electrolysis process here, okay? Because water, okay, I'm going to put water out down here, can be, you can't actually see that, we'll pause that. So water, H2O, it, when converted into its ions, okay, it will form OH minus and H plus as two separate ions. And they too will be attracted to the cathode and anode respectively. Okay, so let's draw that on as well. So as you can see, I've shown the OH minus ions going towards the positive anode because they're oppositely charged and they're attracted by electrostatic force. And I've drawn the H plus hydrogen ions attracted to the negative cathode. And again, when they lose their charge, the hydrogen ions will convert into diatomic hydrogen, which will gas off, okay? It will come off as bubbles. Okay, so on this side, at the cathode, the negative charge, we will have a gas being emitted, which is hydrogen gas. On the positive anode side, we will have chlorine gas being emitted or discharged. So both sides here will be bubbling away, producing gases. And hydrogen gas and chlorine gas, neither's ideal. You can test for them. There's various methods of testing, so I'm not going to worry too much about that for now. So, and you can see what's happening here. And I've coloured these in purple and red respectively, because if you recall from our acids and alkalis lessons, a long time back probably, hydrogen ions are positively charged, they are acids, and OH minus hydroxide ions are negative charged, they produce alkalis. Well, if we're losing all our hydrogen ions as hydrogen gas, we're going to get a higher concentration of hydroxide ions, particularly around the anode, which is going to mean that we have a very alkaline solution surrounding the anode. It will immediately around the cathode be quite acid, but then over time, as this completes, then there's less and less hydrogen ions in this electrolyte. Eventually, this solution on average will become less acidic and more alkaline. Now we should write in here what our electrolyte is made up of. So the electrolyte is aqueous, which means dissolved in water. So aqueous sodium chloride. Okay, so that's sodium chloride dissolved in water, which makes it a dissolved ionic substance. Okay, and so we have here everything that's happening. Now, remembering the travel of electrons, let's put that in now. So our electrons are travelling towards the positive terminal. Okay, so our current is going this way, and our electrons in the liquid are going this way. Okay, so our negative charges are moving in this direction. Now our ions move in both directions. Okay, so we're going to label this as the electrons. So this is the movement of electrons making the current flow. Okay, so this is the electron flow, or in fact, really it's the flow of negative charge. Okay, so let's talk about reduction and oxidation now. So we have got oxidation and reduction occurring here. At the negative cathode, we have positive ions that are attracted to the negative cathode, and they are gaining electrons. So reduction is occurring here, okay? So we've written that reduction occurs at the cathode as the positive ions have gained electrons. So if you want to write that down, please. And we have oxidation occurs here at the anode as the negative ions lose electrons. I'm going to zoom out of this so you can see everything that we've done on this diagram. It's quite complex, so try and follow it from start to finish if you can. Okay, so make sure you've got everything written down there. Pause the video if you need to. So we're moving on to page 9, the electrolysis of molten ionic compounds. So when a simple ionic compound, such as lead bromide, is electrolyzed in the molten state using inert electrodes, such as graphite or platinum, which is so that they don't react with the products of electrolysis, the metal, in this case lead, is produced at the cathode, and the non-metal, in this case bromine, is produced at the anode. Lead bromide can be considered as a binary compound because it only contains 2 elements. Okay, so a binary compound is something that contains 2 elements. And lead bromide is an example of how we do this. And you should note that we try and use inert electrodes wherever possible so they don't react with the products. Those examples of those electrodes would be graphite or platinum. So we have some videos to watch now. Okay, so if you've got a digital copy of the booklet, you can just click these links. They'll take you straight to the videos. If not, open up YouTube on your browser and type in electrolysis of molten compounds and look for the Fuse School video. And then electrolysis of molten lead bromide for the second video, and that's a GCSE science revision video. And these are the topics. Sorry, these are the channels which you'll find those on. So pause the video whilst you watch the YouTube clips. Okay, so hopefully you have a better understanding now of electrolysis. So potassium, so it's a checkpoint question here. So potassium is extracted from its ore by electrolysis. That's not tis ore, that's its. Bit of an error there. So question A, suggest why electrolysis is used to extract potassium. And that's for 1 mark. Question 2, in the electrolysis of molten potassium sulfate, name the electrode that the solid potassium metal will form at, for 1 mark. Part C, the electrolysis of molten potassium sulfate is expensive and it's an expensive industrial process. Give a reason why. And part D, aqueous potassium sulfate, so that means dissolved in water, can also be electrolyzed. This is for higher tier students only. Write the half equations for the electrolysis of aqueous potassium sulfate. And that is 6 marks. So pause the video whilst you have a go at that, please. Okay, so let's go through those. Question A, why is electrolysis used to extract potassium? Well, that's because it's too reactive to extract by reduction, that's all with carbon. So anything about it being too reactive will get you the mark. So it's going to react with carbon, it's not going to be extracted by it, it's just going to react with it, so it's too reactive. B, in the electrolysis of molten potassium sulfate, name the electrode that the solid potassium metal will form at. So that's the cathode, or if you've written negative electrode or just negative, that's fine, you can have the mark as well. Question C, the electrolysis of molten potassium sulfate is an expensive industrial process. Give a reason why. Well, that's because it requires a lot of energy to melt the potassium sulfate. So there's 2 things required to get this mark. First of all, it needs lots of energy, and secondly, the reason for that energy. So the energy is required to melt the potassium sulfate. Okay, and then part D, this was a higher tier question. So it wants the half equations for the electrolysis of aqueous potassium sulfate. So at the cathode, okay, so you can have a mark if you've got the correct equation with this cathode. Now, it doesn't have to be perfect. If you've got H plus E minus turns into H, and that's capital H at both sides, H plus E minus turns into H, then you can have a mark for that. Okay, and as long as you've identified that that's the cathode. Okay, if you haven't identified that it's cathode, that's fine, as long as you've written the equation. The second mark for this is for having a balanced equation. So 2H plus 2E minus turns into H2. That's your second mark. And the third one is for the state symbol. So it must be aqueous for the hydrogen ions, the H plus, and the electrons don't have a state, and the hydrogen is gas. Okay, so that's your third mark. Now, you cannot get all 3 marks if you have not identified this equation to be for the cathode, okay? So each of those marks is independent, but you will only get 2 out of 3 unless you've said that it's for the cathode. Now, the equation for the anode is this one here. Now, you can have the first mark for saying OH minus turns into O, capital O, doesn't have to be O2, if you have, that's fine, plus H2O plus E minus, okay? So you can have it for just saying that. The second mark here is for getting it correctly balanced. So that's 4OH minus turns into O2 plus 2H2O plus 4E minus. That's for your second mark. And the third mark, again, is for the state symbols. So the OH minus is aqueous, the O2 is a gas, H2O is a liquid, and electrons don't have a state. So again, that's a mark out of 3 for the anode equation, but you cannot get all 3 marks if you haven't identified that this equation is for the anode. So you can get a maximum of 2 out of 3 if you haven't said that this is for the anode. Okay, so if you've written it exactly like this, you can have 6 marks for this question. If not, if you haven't written cathode and anode at all, you can get a maximum of 4 marks. Okay, so you've done very well, to be honest, if you've got 3 or more for this, because that was very tricky. Okay, so there are 6 marks for this question D, and 1 mark each for the rest. So that's a total out of 9. So give yourself a mark out of 9, please. So moving on to page 10, we're doing an exercise here in labelling the electrolysis of molten lead bromide. So I want you to have a go and see what you can label in this. Okay, make sure you label the cathode and anode at a bare minimum. Carefully look at whether these are ions or whether they are atoms, and indicate what's happened. Talk about oxidation, reduction. Use the last diagram we did together as a template for this. Okay, so you should be able to identify quite a few things that we've labelled on that previous diagram that could be labelled on this diagram. Pause the video whilst you have a go at that, and then we'll go through it together. Okay, so let's go through that. Make sure that you've added all these annotations. So we've got the DC supply, we've got the anode which is positively charged, and the cathode which is negatively charged. I've added some positive symbols to represent the positive charge on the anode. We have the direction of flow of electrons, and then we have electrons flowing here as well. We have reduction of the positive ions of lead to solid lead. We have the oxidation of bromine ions to bromine gas as a diatomic molecule, which is gassing off here. Okay, so if you can make sure you've got all of those, please. Then pause the video whilst you need to do that. Then once you've done that, we're going to move on to the questions below. Okay, I'd like you to have a go at those questions, please. Okay, so let's go through those. So where do the lead ions move to? Well, they move to the negative cathode. Where do the bromide ions move to? They move to the positive anode. Where does oxidation happen? Well, it happens at the positive anode. And where does reduction happen? At the negative cathode. Describe what happens to the bromide ions after they react at the electrode. Well, they lose an electron, which is oxidation, and then they turn into bromine gas, Br2. Okay, so that's not necessary for the mark. Okay, but they turn into a gas, or Br2. So there's 2 marks available for this one. Okay, for the next one there's also 2 marks. So what happens to the lead ions after they react at the electrode? Well, they gain 2 electrons. Make sure you've identified that it gains 2 electrons, and that's reduction. You don't need the mark. You don't need to say that to get the mark. Then they turn into solid lead atoms, or they just turn into atomic or atoms, or neutral atoms, something like that. Then explain why the lead and bromide ions can't move freely in the electrolyte. Well, the ionic bonds have been broken, okay, so ionic bonds have been broken, and that's because of heating and dissolving. Either of those is fine. Okay, so heating and or dissolving, either of them is fine. Again, that's another 2-mark question. Name the type of bond forming the Br2 molecule. Well, that's covalent bonds. And there is 1 more mark on the next page, so if you haven't done it, go to the next page, pause the video whilst you do the next question, and then we can move on. So the last question is explain why the lead atoms have a neutral charge, and that's because they have the same number of protons and electrons, and that's just 1 mark. So there are 12 marks available for this, so give yourself a mark out of 12, please. So moving on, we're going to have a look at atom economy. So in industry, chemical reactions are performed to make a desired product. Okay, any other products are considered a waste. Chemists can calculate the amount of useful product made as a percentage. Okay, the following formula is used to calculate atom economy, and this is the formula here. Okay, I'm going to go around it in a big bubble with my little pink highlighter. So atom economy, which is given with percentage as the units. Okay, so it's just a percentage, it's not really got units, it's just a percentage. So atom economy is equal to the relative formula mass of the useful product divided by the relative formula mass of all the reactants. So that's a ratio there, and we're going to multiply that whole thing by 100 to turn it into a percentage. Okay, so make sure you've got that down. Then we're going to have a go by doing an example of this with a lead bromide. Okay, so for the example, the electrolysis of lead bromide, PbBr2. Okay, now lead is 207 for its relative mass, and bromine has 80. Now, this time our useful product is lead, okay? So they haven't actually told us that, so our useful product is the lead, okay? So that's what we want. That's what they're looking for with this reaction. So we take our relative formula mass of the useful product, which is 207 for the lead. We divide it by the relative formula mass for all the reactants, which is 207 plus 80, and it's Br2, so it's 2 lots of 80, which gives us 367. We then multiply this by 100, which gives us an answer of 56.4%. And as I said earlier, lead is the useful product. So 56.4 of that product is going to be useful. Okay, so there's a video on this for you to watch. So what you need to do, I'll just move that up, is we're going to watch the Fuse School video, What is the atom economy? It's on YouTube. You can either click this link or search for that on YouTube. Pause the video whilst you go watch that clip on YouTube, please. So hopefully you have a much better understanding of how atom economy works. We're going to look at that again at some point, so don't panic too much if you didn't fully understand it. So we're going to move on to the knowledge check now. Okay, we're on page 12. I'd like you to complete all 8 questions in the knowledge check, please. Pause the video whilst you do that, and then we'll go through them. Okay, so let's go through those. Question 1, state the name of the positive electrode. Well, that would be the anode. Question 2, name the liquid that has free moving ions. That's the electrolyte. Question 3, explain why inert electrodes are used in electrolysis. Well, that is so they don't react with the products of the electrolysis. Question 4, state the name of the negative electrode. That's the cathode. Question 5, state where the moving electrons are found. Well, that's in the circuit, or you could have put in the wires and solution. Either would be fine, just 1 mark there. Question 6, describe 2 ways to make ions free to move in a compound. So heating and dissolving. You'll need both for the mark there. Question 7, explain why lead bromide is a binary molecule, and that's because it only has 2 elements. Question 8, state the type of current used in electrolysis. Well, that's DC or direct current. Either is good for the mark. So give yourself a mark there out of 8. Okay, so we're going to move on now to the application of knowledge questions. There's quite a few. Okay, so there's 3 of them. I want you to have a go at those questions. Pause the video while you complete that, please. Okay, so let's go through those. Question 1, explain why electrolysis can be called a redox reaction. Well, first of all, it's a redox reaction because both oxidation and reduction occur at the same time. If you've written that, you can have a mark. Saying redox is much quicker and easier than saying the phrase above. You can have a second mark if you've written that. So to say redox is quicker or easier than saying this statement here, okay, which is quite long-winded, okay, because redox means that. So that's out of 2. Question 2, describe how to extract zinc from zinc chloride using electrolysis. So it's a multi-stage thing, this one. So first of all, you're going to heat it until molten. Then you're going to use a DC current and 2 inert electrodes. Okay, so DC current's worth a mark, 2 inert electrodes worth a mark. Heating it until molten is worth a mark. And then you're going to insert those electrons into the molten zinc chloride. Okay, so saying this point here is worth another mark. So we're up to 4 already. Then you can say that zinc ions are formed at the cathode. You might say that chloride ions are formed at the anode. Both of those are worth a mark each. Then if you've written that zinc will form at the cathode, that is also worth a mark. So 1, 2, 3, 4, 5, 6, 7 here. So this is out of 6. So there's 7 opportunities to earn up to 6 marks there. Okay, and finally, calculate the atom economy of the reaction in question 2. Okay, so I'm going to give you a hint here if you didn't find a periodic table. Zinc has the atomic mass of 65, and chlorine has a relative atomic mass of 35.5. So use that to help you. Pause the video if you need that still to work that out. If you've worked that out, we'll carry on. So the answer to that one then is to do 65 divided by the total, so that's the atomic mass of the useful product, which is the zinc, divided by the total atomic mass, which is 65 for the zinc, plus 2 lots of 35.5 for the chlorine, because it's zinc chloride, ZnCl2. And that equals 65 divided by 135, and that's 0.48. Now I forgot to put the times of that 100 in, so as you can see I've done it afterwards. You can do it however you want, but 0.48 times 100 is 48%. So you get a mark for getting to this stage here, and you get a mark for turning it into 48%. So 2 marks there. In fact, I'll give you 3 marks because I'm going to give you a mark for getting the right number here as well. So a mark for using the equation correctly and a mark for putting the correct number in. Okay, so 3 marks there. Right, we're going to move on to the extension activity. So the extension activity is suggest why electrolysis of lead bromide can be an expensive process. So if you want to pause the video whilst you do that, and I will share the answer with you in just a minute when you're done. Okay, so here's our answer. First of all, it requires a lot of energy to melt the lead bromide for 1 mark. It also requires a lot of energy to run the electricity for the electrolysis for a 2nd mark. And the idea that energy is expensive to buy or expensive to create. So that's out of 3 marks there. Okay, so we're going to move on to the very last thing, which is our keywords for this lesson. So you'll need to learn each of these keywords and their definitions. It doesn't have to be a word for word definition, but it needs to be very close to it, using the keywords each time, which are in capitalized letters. Okay, so that is the end of our lesson. If you have any questions about that, please feel free to email me or ask your teacher or email your teacher. We'll be very happy to help you with any questions you have. Thank you very much.